Hello and welcome to the Interference Technology webinar, Cost-Effective Use of Close Field Probing Part 2. My name is Belinda Stashukevich and I'm the editor of Interference Technology. Established in 1970, Interference Technology helps EMI and EMC engineers find solutions to their various testing, design, application, and regulatory issues by publishing articles, news, and other practical content. This webinar today is presented by Keith Armstrong. Keith graduated from Imperial College London in 1972 with a Bachelor of Science in Electrical Engineering, specializing in analog circuit design and electromagnetic field theory. He formed Cherry Clough Consultants Limited in 1990, which provides design services to help achieve compliance with EMC. They currently have nearly 800 satisfied customers in almost all areas where electronics are used. This webinar is the second in a series of 2. View cost-effective use of close field probing Part 1 on our website, www.interferencetechnology.com. This webinar will be interactive. You will be able to ask questions and answer polls, and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the box on the right-hand corner of your screen. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or to report an issue, click the hand icon. We will present the topic for 45 minutes, followed by a 15-minute question and answer session. Now Keith will begin the presentation.
Thank you, Belinda. Welcome everybody to part 2 of this close field probing webinar. Part 1 was on change screen mode. There we go. Okay, part 1 we did in November when the winter was coming in, and now the winter's going out. We're looking forward to summer. So in part 1 we talked about the principles of close field probing, how to make them, how to buy them, what kind of low-cost spectrum analyzers you can use, and some other types of probes like current clamps and pin probes. A little bit of detail on using close field probes. So we're going to go into that in more detail now, how to use them. So let's look at measuring radiating conducted emissions. Now I realize the title's a bit wrong because we don't really measure in the sense of measure against absolute standards. It's more a question of monitoring or checking, if you like. So we set our spectrum analyzer's input attenuator to 0 dB. Its default is usually -10. Because the close field probes aren't very sensitive and they don't have much output, so we want to get the best signal to noise ratio we can. Set the desired frequency range, and if we're trying to correlate with laboratory tests, set the same resolution bandwidth and video bandwidth on the spectrum analyzer to get something that compares. And then connect the probe and move it all over the surface of the equipment while it's operating, of course. Don't forget to keep it switched on. If it's a magnetic field probe, then we need to use all 3 90-degree orientations, paying particular attention to seams, joints, hinges, gaskets, displays, controls, basically all the points where we tend to get leakages. And do the same thing on the surfaces of connectors and conductors. Ideally, you would see nothing. You just see the noise. If you see the noise, then you've got a good design. I mean the noise floor, that is, of the analyzer. So while we're wiping our probe around over the surface, and especially the joints and seams, we watch the analyzer screen and identify the locations that measure the highest levels of the frequencies we're concerned about. If we're probing a bare printed circuit board, we find we always get strong fields close to any digital ICs or PCB traces carrying signals, but often they don't contribute to emissions. The point is that if you pull the probe away from the device, by the time you've got to be 1 inch or 2 inches away, you should see very low levels of signal. You see, all electronic or electrical signals or power are propagating electromagnetic waves guided by the traces or by the metallization of silicon or whatever. So when you stick your probe into that region, you pick up the actual signal portion of it. But we want those waves to stay close. We don't want them leaking out because that gives us emissions and immunity problems. So we hold the probe 1 inch or 2 away, and hopefully we see nothing. If we do see something, it means we could have a problem. But it's difficult, of course, to maintain a fixed spacing by hand while watching the analyzer screen. So what we might do is encapsulate a probe in a block of epoxy or acrylic with the right dimensions, and then press the surface of the encapsulation against the thing we're testing to ensure the correct spacing. That would be more for a printed circuit board rather than the seam or joint of a case, for instance. So there's our probe, one of the ones we talked about last time, and there's an example of potting it in a clear acrylic. Good, eh? But you don't have to use that. You could just take your regular probe and just tie wrap on a couple of blocks of polystyrene of the right thickness or something. Don't use anything really solid, like heavy-duty plastic or something. So another solution, which is more appropriate if you're checking a lot of things in, say, a production environment, checking that everything has the same sort of signature, which we'll talk about in a minute, would be to use an industrial robot. So we program it to check our printed circuit boards, for instance. Now, there's other kinds of probes, some which are like flatbed probes. You put the PCB down and you get a colored image of the near fields at some centimeters away from the bottom of the board. That would work too. It takes about the same kind of time as scanning a probe over the surface. So there's various solutions to this. You don't always have to hold the close field probes by hand. If you're looking for problems, and a quick scan over the joints and the conductors and things, the cables, will often reveal the main sources of emissions, which can then be investigated more closely. If you're comparing one device or board or equipment with another, then we have to have a fixed routine, a procedure for moving the probe over the joints, displays, controls, etc., using the various orientations. As I said last time, if you remember, probes are very well, their sensitivity varies depending on where you are on the probe. And so it matters very much how you repeat your holding of the probe. That's why a robot is particularly good, because it'll always repeat what you programmed it to do. One of the handy things is to get a signature for emissions, and later on we'll talk about an immunity signature. We put the analyzer into peak hold mode, go through our fixed routine, scanning the probe over the surface. And the final display on the analyzer is the signature for the item. We can use that then to compare with other items. This is useful for testing effects of modifications, like a software bug fix, for instance. Did it make a problem for emissions? It can do. Or a hardware, a device substitution, maybe some parts gone obsolete. We want to see if a replacement part would give us the same kind of electromagnetic signature. But it's very important to always use exactly the same probe. And if you've dinged it, then it's no good. You've got to go get your signature again, because putting a bend in it or something will affect its performance. The same cables, the same spectrum analyzer, the same test bench setup, and of course the same procedure. It helps also to have a particular known source of noise, like your laptop, for instance. You might find that in a particular area of the touch pad, you can see noise on your close field probe, and so it's worthwhile checking that you just hold the probe by the touchpad in the right place and check that you get the same thing that you're used to seeing, because sometimes connectors, RF connectors can fail, for instance. I've seen that happen. And you spend a long time thinking, oh, we've made it really good, when in fact all it is the connector's broken. So we can get better discrimination from our signatures by getting a number of peak hold signatures for each product covering different parts. We might have a signature for the keyboard, a procedure for moving the probe over the keyboard, a signature for the display, a signature for the connector panel, the case seams, the mains or DC power cable, the Ethernet cable and its connector, and so on. And that helps you check whether things have changed. It's not all mushed up into one peak held spectrum. It's different spectrums for each thing, so that can help too. For conducted emissions, we do the same thing, except we generally set the analyzer to a different frequency range. We might use larger probes because they're more sensitive. We don't use large probes for high frequencies because they might resonate due to their dimensions. when we're measuring conducted emissions, we hold the probe against the jacket, the insulation of the cable we're checking, close to where it enters or exits the equipment, say less than 4 inches away. So, and find the worst case. Now, if your filters and shielding are working properly, then you shouldn't see any untoward noise on the cable at that point. One of the problems with measuring emissions is overloading the spectrum analyzer input and getting into modulation. This can happen due to strong signals which are way outside the frequency range that we're measuring. For instance, say you're measuring 50 megahertz to 300 megahertz, just for argument's sake, and that's the scale you're looking at, but you've got a DC-DC converter or an AC-DC converter that is putting out a strong emission, maybe even below the frequency range that you care about for passing the tests. For instance, if commercial tests, emissions test starts at 150 kilohertz, you might well have quite a strong signal at 50 kilohertz. But it's not measured by the test, so we don't care about it for compliance. It could still cause interference though, so maybe we need to care about it from that point of view. But that 50 kilohertz is getting straight into the analyzer, and the spectrum analyzer doesn't have a filter on its front end. There's a mixer right on the back of the RF connector, and so you can get overload due to the 50 kilohertz, even though your lowest frequency that you're scanning is 50 megahertz. And the result can be noise on the screen, which is meaningless noise. It's noise caused by artifacts in the analyzer. If you think this might be happening, then we don't use the analyzer's attenuator, because that happens after the mixer, and so it doesn't get rid of the intermodulation, the overload. What we do is put an external through-line attenuator. This will be one that connects in between the cable from the probe and the input to the analyzer. It's got our BNC or N-type connectors on it for that purpose. If your signals that you see on the screen were valid ones, they'll reduce by the attenuation of the attenuator, the through-line attenuator. It doesn't have to be a 10 dB attenuator. I could have said X dB. It could be 6, it could be 3, it could be 20, whatever. The point is, if they're valid signals, they'll reduce by the amount that the attenuator is supposed to give. If they're not valid signals, intermodulation for instance, then they'll reduce by 2, 3, or 4 times as much. So say you had a 3 dB attenuator, the emissions, the real emissions you'd expect to go down by 3 dB, but the intermodulation would go down by at least 6. That often isn't awfully clear with a closed field probe, because we can easily get 3 dB variations just by holding the probe differently. So it's better to use something like a 10 or 12 or 20 dB and see. If the noise spectrum you measure looks exactly the same after you put a 10 dB attenuator in series, except it's 10 dBs lower on the screen, then it's all valid. If some of the noise appears to disappear, if you see what I mean, then we need to perhaps put a filter in the series. So let's imagine we've got our very strong 50 kilohertz DC-DC noise, and we can make a little box and put a little put a filter in it. It could be a high-pass filter. If we're interested in measuring above 50 megahertz, for instance, we might make the filter be 3 dBs down at, say, 5 megahertz. Just a minute. Or we might have a bandpass filter, a band reject filter that we tune to the exact frequency that the noise is at. You can buy so-called pre-selectors. Basically, they're variable bandpass filters that follow the spectrum analyzer's measuring frequency. All the ones I've seen aren't portable, though, and need connecting to the analyzer's GPIB bus. So we're talking here about more expensive bench instruments. Or we might use an EMC receiver instead of a spectrum analyzer. Now, I always use spectrum analyzers because all of the receivers that I've seen, which have a tuned radio frequency stage before the mixer, are rather slow for the kind of diagnostics you do with a spectrum analyzer. So I don't tend to do that. But if you have a receiver handy, you might choose to do that. So, what about immunity? We can use a wide variety of signal generators with our close field probes to create localized, quite powerful magnetic or electric fields. We might use transient generators, ESD generators, fast transient bursts or ESD, or radio frequency generators with the appropriate modulation frequency sweep capabilities, for instance, to test to like the ones used for testing 61043 or -6, or the equivalent military standards, or automotive standards for that matter. Some people automatically fit 50 ohm resistors in series with loop probes or in parallel with electric field probes. But if you're just using an ordinary signal generator, then they'll work happily into a short or an open circuit. The same isn't true if you're using a radio frequency power amplifier to get a bit more stronger field, and we'll talk about that in a minute. So if we're interested in a particular kind of phenomenon, then we choose a source that corresponds to it, and we set the source up accordingly. We might, for instance, for an RF signal, sweep over the frequency range with using 1 kilohertz sine wave amplitude modulation at 80% depth to compare with the regular commercial standards. If we're doing military or automotive testing, we might use different modulations according to the kind of test we expect our product to be put through at the end. It's important to set the test signal at a low level before connecting the probe to the output of our source, and then we need to talk about power amplifiers. Usually an ordinary signal generator has enough power to test individual devices on a printed circuit board with close field or pin probes, but if you want to, for instance, check the immunity to test corresponding to conducted immunity, like 61046, we're going to use a clamp-on probe, current probe, and clamp it onto the various cables. And you generally need to boost that with an RF power amplifier. In fact, if you want to get up to levels comparable with industrial standards, never mind automotive or military standards for bulk current injection, you're going to need about 200 watts. In fact, with bulk current injection using a clamp-on current probe, it's quite easy to do a fairly realistic test yourself, bearing in mind that even BCI tests in regular labs are quite variable unless you take great care. Anyway, where we've got a power amplifier, even if it's just like a little 5 watt module or something, we always should connect a suitably powerful 50 ohm RF resistor, either in series with a close field probe, a loop probe, that's a magnetic probe, because otherwise it looks like a short circuit, or in parallel with an electric field probe, because otherwise it looks like an open circuit. Because many power amplifiers will be damaged if you don't load them with something like 50 ohms. Amplifier research have built their whole business on the idea that the amplifier should work into any load. But even so, I wouldn't want to run my AR amplifier into what I knew was a perfect short circuit at low frequencies, for instance. That's not a wise thing to do. Anyway, just a point on the powerful resistor. If you've got a 200 watt amplifier, you need a 200 watt rated resistor, and it's going to have heat sinks on it, and it may need a fan blowing on it to keep it cool enough. Okay, bear that in mind. And always take all safety precautions using any immunity test equipment or radio frequency power. Not many people realize that if you put a signal generator with an N-type output, you put it on a shelf at about eye level, and you look at the N-type, if you look at the center pin of the N-type from, say, a foot or two away, if the signal generator is set to a high level and a microwave frequency, you can actually damage your eye. The N-type connector isn't a very efficient antenna. It's a very narrow beam, but if you're looking straight at it, your eye is right on that beam. So there are a variety of safety requirements associated with radio frequency power. And if you don't know what they are, then find out. Very important. Don't think that you must know what it's about, okay? Because unless you've actually read the stuff or been on the training course, then you don't know what it's about. So for radiated immunity, we'd move the probe of the equipment just like we did for radiated emissions. It's the inverse, if you like. We observe the functions of the equipment being used for any errors or malfunctions. If we don't see any problems, then we increase the test level and do it all over again. Keep going till we find some problems, or till we run out of power. And, you know, we know that at that kind of power level, we have the experience of saying, well, if we don't have any problems with this test procedure at this power setting, then when the thing is tested for immunity in a test lab, it's going to be all right. So you're always doing this comparison between test lab measurements and your own close field probe measurements. And it means that over time you can reduce the amount of test lab testing that you're doing because you know what you're going to find. If you're using swept RF, then the sweep rate should be slow enough for the equipment to respond. You know, if it's video or audio, then you'll see or hear the effect straight away. But if it's some kind of instrumentation, there's often some kind of time lag involved. Maybe there's some averaging going on, or just a big time constant. So you might have to sweep so slowly or have a long delay at each step that you have to move the probe very slowly. You know, it's a good idea to have the probe in a clamp, actually. Clamp it in one place, let the analyzer go through its programmed sweep over the frequency range, stepping at the appropriate rate, and then move the clamp to position the probe somewhere else and do it again. If you try and hold your hand in that position, it's going to get very tired very quickly. You might use a smaller sweep frequency range, and to take the same amount of time overall, it just means that you have the probe, you can move the probe around more quickly. So we can get a signature for immunity just like we did for emissions. We go through our fixed routine in exactly the same way each time, and the highest signal level we can set, given the source that we've chosen, before the function performance becomes acceptable, becomes a signature for that test item. And we can compare signatures for significant differences, just like for radiated emissions or conducted emissions. It's useful for testing the effects of modifications. For instance, if somebody says, oh, you know, we've got this new version, next version of the software, will it cause any EMC problems? Well, of course you don't know, but it's very quick to just load it into the product and have a quick sweep around checking for emissions. If the emission signature is unchanged or is better, then quite likely the immunity signature will be unchanged or better. No guarantees, guys. Remember, as before, it's always important to use the same probe, the same cables, the same generator, actual generator in the same settings, the same setup, and the same routine every time, because otherwise close field probing is just too variable to say what's going on. For conducted immunity, we follow the same procedure, except that this time, just like for conducted emissions, we hold the probe against the insulating jacket of the cable being tested, close to where the cable enters or exits. Using the same orientation that we found gave the maximum emissions measurement for that product. And again, we prefer larger diameter probes because they're more sensitive to lower frequencies. Now, quite likely, if we're testing cables, we prefer to use a clip-on probe, like a current clamp. We can test individual devices by holding our probe very close to them, finding the worst case orientation, and that can be quite sensitive. I typically use a 1 centimeter unshielded loop probe to generate electric and magnetic fields at the same time, and I found that even with a 1 centimeter probe, I could clearly distinguish between two TO92 little transistors on a printed circuit board right close to each other. You could tell which was which one was having the problem. So you might think that the probe dimensions are such that you're not going to be able to discriminate smaller than the dimensions, but often you can. Alternative techniques then include using current injection probes, current clamp probes, to inject transient or RF currents directly into cables. It's important to make sure the probe rating is sufficient. If you buy certain of the emission probes that you can buy have little amplifiers in them or aren't rated for use for immunity, if you're making your own with bent bits of wire like I mentioned last time, then you can put power into them, and if you destroy them, well, that's not a big deal. If you paid $1,000 for a current monitoring probe from Fisher Custom Communications, for instance, as other people make probes as well, then you'd be rather upset if you were to burn it out. So you may need, if you're buying current clamp probes, clamp-on cables, you're going to want to buy some for current monitoring and different ones for injecting. I've used injection probes up to 400 watts, and I'm not aware of any that are bigger, although there are some which are embedded in, for instance, lightning test rigs. So we can use pin probes to inject test signals directly into the pins of devices. Important to always start off with a very low test level and then just gradually turn it up, because we don't want to destroy the device straight off. In fact, we don't want to destroy the device at all. We just want to find the point at which it starts to malfunction. If we want to find the worst case sensitivity of a device, it's important to modulate the signal with the kind of frequencies, the same frequencies that the device uses. For instance, if we have a chip that's running, that's taking data from a bus that's clocked at a megahertz, then use a 1 megahertz square wave, or 1 megahertz square wave modulation of a higher frequency. If we've got an analog circuit with a long time constant, like a temperature sensor, then use pulse modulation. So choose what, sweep over the RF frequency range, but just basically pulse on and off with a 1 hertz on, 1 second on, 1 second off, that sort of thing. Now, I was once measuring a hot plate, and this is for a path lab type of hot plate, precise temperature control. We had a beaker of water on it and a mercury in glass thermometer reading 60 degrees, and we wanted to maintain the same temperature. But as an RF immunity test, if you waited until you could see a difference in the thermometer reading, it was going to take at least, I don't know, a minute or two before you saw any difference. So you don't want to dwell at each frequency for a minute. It would take much too long. What we did was put an ammeter in the mains power. Noticed that when it was settled down and stable at 60 degrees in the mercury and glass thermometer, it was drawing about 100 milliamps from the mains, from the line, if you're in America. And we could quickly see, if we interfered with the control system, we quickly see that the current drawn from the mains either immediately reduced or immediately increased long before we saw any temperature change in the beaker of water. So based on the fact that we don't want anything, we don't want to upset it at all, then measuring the mains current was a good way of quickly checking that the device wasn't being upset. There are some people who make noise injector products. Some of the noise injector products that used to be available, sadly the people don't make them anymore, but here's an example of one that I think is still available. You've got these 2 probes. This is meant for probing around on printed circuit boards and directly injecting into traces and devices. The maximum field is around these little tips here. You can set the power, you can set the frequency, you can set the polarity, and here's a nice little calibrator that comes with it to check that it's working properly. So there's several people making these sorts of things. So time for some questions from Belinda.
Okay. We'd like to ask our audience a few questions. Question 1. A close field probe very close to an IC, A, picks up noise, which is the cause of emissions, or B, picks up signals associated with IC operation. We'll give you a few seconds to answer this question. And we have some answers coming in. And about 75% said B, which was the correct answer. Here's another one. To obtain an emission signature, A, the procedure is not important, B, the exact equipment used is not important, or C, the details of the equipment and procedure are important. We'll give you a few seconds. And the 100% of you said C, which is the correct answer. And here's another one. Intermodulation distortion can be detected by A, fitting an external attenuator, or B, using the spectrum analyzer's built-in attenuator. And we have answers coming in. And 90% said A, which was correct. So everybody was pretty much on the money. Back to you, Keith.
Thanks, Belinda. Okay, thank you for showing us that you're all awake and aware and keeping up. Let's look at some uses of close field probes then, some specific uses they might be interested in design or development. We can, for instance, use small probes with oscilloscopes or spectrum analyzers. It helps to be able to relate what you see on the scope to what you see in the spectrum analyzer. You might, for instance, improve decoupling by monitoring the VCC noise. Obviously, we can go into all sorts of detail about these things, but we don't have time in this short webinar. You can, for instance, see if plane splits in planes, obviously, are causing problems. A lot of people will split 0-volt planes when they shouldn't these days. Any advice to split a 0-volt plane is probably about 20, 30 years out of date. The only reason these days for splitting a 0-volt plane is for galvanic isolation. Otherwise, a solid plane usually works the best. To monitor waveforms without making a connection. In the example of a plane, for instance, you might actually tape a probe near the open end of the split and just pick up the noise from the split, and then while you're exercising the equipment, and then see if shorting the split out or linking it with capacitors gets rid of the noise whilst not affecting the operation. You can monitor waveforms without making a connection. It's always a problem if you haven't, say you want to probe very fast rise times, or you want to probe very high frequencies, but you didn't lay the board out, so there's a coaxial connector possibility right at the point where you want to measure the thing. Well, if you don't use a coaxial probe, you're not going to be able to measure high frequencies accurately anyway with an oscilloscope. But with a spectrum analyzer and a close field probe, you just hold the probe right near the thing, and you can see the frequencies without any kind of need for a connection to the circuit. So you can monitor waveforms. Check they're not suffering from too much noise. See if transmission line termination is needed or is good enough. See which pins are associated with mission problems. Langer make a wide range of close field probes. They do some very tiny ones specifically intended for checking pin by pin on small outline devices. And you can check switch mode power converter designs for overshoots and ringing. This is often quite difficult because a lot of people don't have the necessary differential probe amplifiers which will withstand a kilovolt or two, so you can use them for probing around offline switch mode converters. And so what they tend to do is remove the ground or the earth lead from their oscilloscopes and float the earth of the scope, which is very bad. A, you're connecting a very large stray capacitance at some point in the circuit, so you're likely to disturb the circuit. And B, somebody like me who might come in, rest their hand on the oscilloscope and get a nasty shock, and then, you know, die, and my widow sues your company for $1 billion for killing me, you know, because people don't put warning signs on their test equipment. Anyway, don't do it. Okay. Don't float your scopes. Very bad. Never take the ground lead off. If you don't have the differential amplifier with the high voltage withstand capability, then use a close field probe with suitable insulation, of course. You want insulation that will withstand a kilovolt or two, not just something that will withstand 60 volts. There's lots of clever things you can do with close field probing, especially if you have a tracking generator. Here's an example of an old Agilent analyzer. It was introduced in the 90s. Very useful thing and very good. We talked about intermodulation earlier on, and it's almost impossible to overload the receiver input with anything that's sensible anyway. So you don't have to worry so much about intermodulation. It's very rugged, and you can get them on eBay for about a few $1,000s. Anyway, pay a couple more $1,000 and get one with a tracking generator output. We can connect a probe to the receiver input, another probe, doesn't have to be identical, to the generator output, and then we do a sweep and measure the coupling between the two probes. It might look like that. Now, some analyzers will have a zeroing capability where you just press the 0 button and it'll give you a flat line across the stream. But even if you don't, it doesn't matter, because then we put in between the probes the material we're interested in and then do the same sweep we might get that sort of result with the material. And the difference between the two is the shielding effectiveness. And you see it varies with frequency. So you might think, what if we overlap these joints? What if we have screw fixings every 100 millimeters, and we overlap by different amounts? We can make sure that the seam, the joint, is in between the two probes, and have a look, see how much we need to overlap to get a decent shielding effectiveness, for instance. Or experiment with different kinds of gasket, all sorts of things, or just experiment with different kinds of material. What if we're plating plastic? What thickness of plating, what kind of materials do we need to get the shielding effectiveness that we want from the plastic? Another technique then is to fit a probe inside the box, connected to the spectrum analyzer via a bulkhead mounted shielded connector, with the bulkhead mounted in the wall of the shielded box. So we're emitting the tracking generator into the enclosure, and then we have the second probe outside. It says here aligned with the first, but that would be for measuring the shielding effectiveness of that particular part of the shield wall. If you move the probe around, you can have a look at the leakages from seams and joints and all that sort of thing. But you don't have to use a tracking generator. There's all sorts of battery-powered broadband noise emitters you can put inside the shielded box, like these ones from York EMC Limited. There's lots of other people who make these, and you can also make your own. There's guidance on the internet for making your own broadband noise generator that runs off a battery. Put it into a plastic box, put it inside the thing you're testing. There's also other approaches you can use using a directional coupler. The radio hams call these VSWR couplers, or VSWR couplers. It has an input and output and a coupled output. We connect the output of the tracking generator into the directional coupler and then to the probe, get the coupled output into the spectrum analyzer. Now, I'm pretty sure that I think these have to be the other way around. I don't know why. I just bought a directional coupler to start doing this sort of work. There are people who've been doing this for ages, but I've only just got an analyzer with a tracking generator, so I'm just starting to experiment for myself. But I have made it work. I just need to do some more work to be able to amplify this sort of PowerPoint here. So here we've got our straight line across the top of the screen, which is what we get when the probe is positioned, say, across the top of this sheet of metal here. And then we move the probe over the gap, and we get some dips. And these dips indicate that we're losing power. What's happening with the straight line is that all the power is being reflected into the probe. And so we're measuring, on the coupled output, we're measuring a flat spectrum of reflected power. When we put the probe over some imperfection, like this joint here, which isn't perfect, then we find that at certain frequencies, we're losing power, which is indicating that the joint isn't a perfect reflector, although it's not a perfect joint. Typically, you need to set the analyzers to 2 dB per division. It's what I've found so far anyway. And we might only see 4, 6, 8, 10 dB dip here. So it's quite a sensitive measurement, or it's quite, let's say, you have to be quite careful to do it properly, but I'm going to get more experience on this and talk about it more later on. Anyway, there's lots of applications for probing with directional couplers. You might identify a circuit's resonance by the peaks and dips it causes in response, maybe a power supply, power distribution network, this sort of thing. If you've got a passive RFID antenna and you don't have the RFID reader, or you've got the reader and the antenna won't respond, maybe it needs tuning. But you need to pick up the frequency it's tuned to, and then adjust it to the right frequency rather than just adjust around at random, hoping you hit the right frequency. And of course, you can see the frequency using that technique I just showed you with the closed field probe there on the previous slide, and tune them to the right frequency. If you use directional couplers with a clamp, a current clamp instead of a probe, current monitoring clamp, we can measure resonances in cables and metalwork. Well, any metalwork you can clamp the probe around, that is. And you can check, for instance, transmission line terminations. With the probe around the whole cable, we can check the common mode termination, which people often forget. And with the probe around one of the conductors in the cable, we can check the differential mode, transmission line termination. We can check cable shield terminations at one or both ends, and we can check the structural resonances of buildings by clamping usually a fairly big probe around some piece of metalwork. And we can use probes at every stage of the project. For instance, the proof of design principle stage. I've now and again seen people with products that they couldn't make pass the EMC tests, and it turned out that the actual approach they'd taken to designing this product was incorrect. Well, they didn't know it was incorrect. It's only when they came to test it for EMC that they found that it was going to cost a lot more to make it EMC compliant and legally sellable than they'd budgeted for, and it would be too expensive for the market they were aiming it at. So in other words, all their time was wasted. Now you can check this out on a breadboard. You've got some kind of breadboard proof of principle. Just wave a probe around and see how much noise you get. And if you get a lot of noise, then it's telling you you've got to do a lot of shielding or filtering or something like that, or do something anyway. Don't leave it till the end of the project. So you can save yourself, quite literally, you can save companies millions, tens of millions of dollars just by having a quick wave of a probe around some new design. And this could be a hardware or software issue. It's very easy to do what-if experiments with close-field probes. See, we're not doing an absolute measurement like in a test lab. We're just saying, is this better than that? Or is this particularly noisy? You know, are we going to have to... I mean, I saw one thing, somebody made a printed circuit board, and with the probe 4 feet away, this is a 1 centimeter probe, 4 feet away, the spectrum analyzer was still showing significant levels. Now, with a product like that, printed circuit board like that, it was going to need, you know, military-style shielding boxes to get it past even the commercial tests. So you can say straight off, no, this is a bad idea. The way that's constructed is just bad. You know, don't even go down that route. And you can tell this with a bit of bent wire that you made yourself and plugged into your spectrum analyzer. Talk about getting a good bang for your buck, eh? So one of the things is, when we're doing good EMC design, if you've read any of my articles or books or whatever, or attended any of my training courses, you'll know that a lot of it depends upon the wavelength. And the wavelength, or the shortest wavelength that you need to control. The shortest wavelength, of course, is associated with the highest frequency that we care about. This may not be the highest frequency we test to. It might be higher or lower. We need to know what the highest frequency of concern is in order to design things cost effectively. These are usually associated with the rise and fall times of the digital circuits, the switch mode circuits, pulse width modulation, all that sort of thing. But quite often the data sheets don't include that sort of information. They might include for digital devices anyway, the maximum rise and fall times, but what we want to know is the minimum values. How fast are they actually going? Close-field probing very quickly finds the highest frequencies of concern for emissions and immunity. So it's a good thing to do early on while you're figuring out how to design the product before you start the actual design. When you're doing design, it's a good idea making some experimental test boards or experimental assemblies to check out the alternative design approaches before committing a lot of design effort. Once again, with a little bit of bent wire or a probe that costs a few $100s, you can save your company millions of dollars, maybe tens of millions of dollars or euros if you prefer. Especially if you're adopting a new technology, new types of microprocessors, new types of power switching devices. This is particularly relevant actually, because I was just reading the other day, in the power switching world, they're rapidly moving on to silicon carbide FETs and IGBTs and equivalent devices, and gallium nitride FETs and IGBTs and other equivalents. Some of the equivalents don't exist in the silicon world, but they switch 10, 20 times faster. So if you're using these new switching devices, you're going to be having problems with frequency ranges that your company doesn't have expertise in. You know, so and there's always new lessons to learn. So it's very important to learn these lessons before you start the design or during the early stages of the design when design changes cost less. You don't want to be going to a test lab and find out you've got a problem when you're like a week or two away from launching the product. Okay, that's a bad project management. For selecting components, we find that some apparently identical ICs have much worse emissions or immunity than others. I've seen more than 40 dBs difference between equivalent microprocessors. These are two products doing the same job with the same package, same clock frequency. I don't know why this company had got two different microprocessors, but they had. Same kind of printed circuit board. One of them required tin canning on the board, even to the extent that a 4mm diameter hole in the tin can was too much. The other type, and that just about scraped in, by the way, on its tests, the other type, you couldn't even tell it was switched on. Now, which type of microprocessor do you want to design with? The one that requires heroic efforts and added cost and delay, or the one that just is like a pussycat and just behaves itself? Well, I know which one I'd rather use, and you can very quickly identify which ICs to avoid by close field probing. Now here we would directly probe the IC. We'd hold our probe right against the surface of the IC. Either get a selection of manufacturers' evaluation boards or make an experimental board. It's well worth it. A lot of people think, oh, we're trying to save cost in development, so let's not spend money on evaluating stuff, which is, of course, a very bad error of judgment. If you're not sure, then build yourself an experimental board. It doesn't have to be like the final board. You just want to get the chip working, because you're going to hold the probe smack against the chip, so it hardly matters what the printed circuit board is like. Okay? You just want to see the internal workings of the chip, see what kinds of levels and what kinds of frequencies are being used in the chip. And that tells you how your EMC design has got to go in order to use that chip effectively. Within a few minutes, if you had a bunch of, say you had five manufacturers' evaluation boards in front of you, all plugged into their power supplies, within a few minutes you can tell which probes you want to avoid, which ICs you want to avoid, and which ones you want to use. Within a few minutes. Why wouldn't you do that? Very cost effective. In product development, now ideally we wouldn't have any product development. You just design it and it would work right first time, and that's what we should aim for. But nevertheless, we usually end up trying to figure out what's gone wrong, and closed field probes can very quickly find errors in PCB layout, in traces and planes, in IC power supply noise and decoupling, in the way the shielding has been implemented, in the way the filtering has been implemented. Quite often people think that the filter is going to work perfectly well on its own, when it doesn't. Okay, a filter always has to be connected with a low impedance to the radio frequency reference. People think that shielding, you just get a shielding box and then you've got shielding. No, not unless you've done a load of other stuff properly, and close field probing will find out if you've done the other stuff properly. Then there's a wiring harness, actual construction, and the types of cables. Maybe you farmed some work out to a subcontractor. You can check whether they did a good job or not. Cable shield and filter bonding methods. Connectors and glands, are they good enough? Have they been assembled properly? Was the paint removed? Did the metal manufacturer, person who supplied the metal work, put an invisible polymer film on so your gaskets don't work properly? That's a common problem, and so on. Then we've moved on to having a test failure. Now, if you use good design techniques and close field probing throughout a project, you shouldn't have any compliance test failures. You should know when you put your product in for compliance testing that it's going to pass, okay? And it's cost effective. Simulation can also help with this too. But anyway, let's say we do have a compliance test failure. We don't know where it's from, but we do know what frequency it's at. And it's very tempting to scan at that frequency only. The trouble with that is that if we fix the problem on frequency, we often find we haven't fixed it, we've just tuned it, so it pops up at a different frequency. So a good idea, and I've learned this the hard way, like most of the stuff that I've learned, by wasting time and money. This is before I became an independent, of course. Then we get a signature over the whole tested range. We talked about getting a signature before. Then we zoom in and squash the problem that we've got at that particular frequency, and then zoom out again and check the whole frequency range to make sure we haven't just moved it to a different frequency. You don't want to go back to the test lab and find that what was a problem at, say, 350 megahertz is now just a problem at 570 megahertz. We want to know that's not the case. In volume manufacture, we find that different batches of ICs can have different EMC performance. And you can identify these quickly at goods in using close field probing techniques. We also find that we can get non-compliance from tolerances in devices, variations in assembly methods, assembly errors, design changes. Somebody may have made a design change and thought that it wasn't going to be important for EMC, or even not thought about it at all, which is more likely. And we can very quickly check for these using emission signatures like we talked about earlier. How much margin? Well, it depends. The margin depends upon the amount you were below the emissions line on the emissions test, or the amount by which you were above the immunity limit by testing at higher levels. At some frequencies you may find that you've got only 2 or 3 dBs of margin, in which case you can't allow much more noise, sorry, I shouldn't say noise. You can't allow much more variation at those frequencies. But if you've got 20 dB below the limit line, then it doesn't matter if you measure variations of 10 dB, does it? Of course, in goods in and volume manufacture, the people using these close field probes won't be skilled testers or know anything about EMC. So what you can do is to make a test fixture that has the probes in certain places, actually, epoxied to the side of the box or whatever, and program the test instruments so they'll do the tests automatically. So all the operator has to do then is to plug in the chip into the ZIF socket or something, select from his menu the type of chip, press start and wait for a green or a red light, or a buzzer if you prefer, and know whether to accept or reject that batch of chips, or if that board has a problem or whatever. Some people, some larger companies, even connect such production EMC test equipment, or I suppose we should call it EMC signature checking equipment, to their main computer system and identify trends in the EMC performance before they become serious issues. Generally speaking, the EMC performance of a product that's in serial manufacture always gets worse with time. I dare say they might get better, but generally speaking they get worse with time. People make design changes, they make component substitutions, and try and save money here and there. And the question is this a big problem for EMC? Well, we can wave our probe around in development, like I said before, or we can test it in production. And generally speaking, you can say, oh look, if we carry on as we're going, then in 6 months we'll be making non-compliant products. So you can take action before you've made a batch of non-compliant products. Because whenever you've made a batch of non-compliant products, scrapping them is a very difficult decision to make. And a lot of managers won't make that decision. They'll just ship them out anyway and hope nobody notices. And why do we care? Now, if with legal compliance issues, if something's a little bit worse than the limit, it's probably not a big deal. Probably not going to get caught. We hope not anyway. But the real issue is not the legal one. The real issue is that the EMC tests that are normally done, certainly in the commercial and industrial world, are just about what you need to make something which is just about acceptable from the point of view of reliability in real life. If you don't meet those tests, you're going to get a lot of them back as warranty repairs, and you're going to annoy a lot of customers. It's going to cost you a lot of money. So that's the real reason why we meet the EMC test. It's not for legal compliance at all. Tell your managers. Very important. What about design changes and component substitutions? Well, we've already touched on these things. We get a signature for something, do the mod, and then get the signature again, for instance using our robot, so we don't make mistakes with the scanning process. We might find that the design change needs more work, filtering, shielding, and we can do those changes and then remeasure. And it might be that the design change isn't accepted because it would require too much work. It might mean that we need to do the design change, but we have to put the product through its compliance tests again because the close field tests are indicating that it might not pass this time, but we're not quite sure. In systems integration and installation, we can check whether the EMC performance has been compromised by poor assembly, for instance. Incorrect filter grounding, incorrect cable shield termination, incorrect types of shielded cables, incorrect routing of cables, missing gaskets or badly assembled gaskets, paint over radio frequency bonding areas, or not so much paint perhaps as some kind of polymer passivation, fixings not done up tight enough or too tight, and so on. And because all our products, all our electronics these days are noisy, nearly all anyway, they're digital circuits, they're switch mode power converter circuits, it means that it's very easy to check just with a spectrum analyzer and a closed field probe, even a handheld spectrum analyzer and a probe. You can very quickly check whether the system has been integrated properly or installed properly, if there's any bad cables in there, somebody's terminated the shields wrongly, not mounted the filters properly. It takes a few seconds to hold the probe against something and say, oh look, there's a problem here. What about in maintenance, repair, and mods and upgrades? Well, the best thing to do is to get a signature for the product, system, or installation when it's new. But quite often, if we've got something that's been in the field a long time, we may not have done this. So at least get a signature before you do the maintenance, modification, or upgrade. And then repeat it afterwards to make sure you haven't made the thing worse. Now, in the case of something that's been in the field a long time where you didn't have an original signature for it, you don't know if it's actually EMC compliant, but the point is, presumably it's working properly, or working well enough, and so you just want to make sure that you haven't made it any worse. Okay, that's the end of the slides, and we have a few poll questions to finish off with.
Okay, we have a couple more questions for our audience. Shields and enclosures can be checked by A, using a spectrum analyzer's tracking generator, B, using a standalone wideband noise emitter, or C, either A or B. And the majority have answered C, either A or B, which is correct. Next question. Devices should be selected on the basis of A, data sheet specifications, B, measurement with close field probes, C, price, or D, all the above, with price being the least important. And most of you have voted, and 97% said D, which is correct. And one more. Close field probes are useful in A, design, development, test laboratories, B, real-life environments, or C, both A and B. And the majority, again, said C, which is correct. So all the attendees got all the questions right. Thank you so much, Keith. We'd like to have a call for final questions from our audience. Please enter any last questions you may have in the navigation pane. We've received quite a few inquiries on where to get additional information on this topic. There's a vast amount of content found on our website, interferencetechnology.com, and Keith's website, cherryclough.com. You can also email us at info@interferencetechnology.com with specific needs, and we can direct you accordingly. Keith, here's a question for you. I have purchased some close field probes and some that I made myself, and they all give different results when measuring the same item in the same way. How can I believe any of them?
Well, remember that with close field probing, we're not doing absolute measurements traceable to standards, which is what a test lab tries to do. That's why test labs have all these special equipment and special setups and things and special chambers. All we're using our probes for is making relative measurements, like signature measurements and things. And as like I said several times, make sure you use the same probe, not the same type of probe, the exact same probe, the exact same cables, the exact same analyzer every time. So yes, the probes, all the probes give different results when you compare one with another. So what we have to do is stick with one probe and make relative measurements. That's that.
Okay, here's another question. I want to use close field probes to find the causes of emission test failures, but my spectrum analyzer does not have quasi-peak or average detectors. Do I need to buy one that has these detectors?
Well, it helps. But mostly we would do our work with a peak detector on anyway, because the quasi-peak detector is so slow. And if you want to scan over a frequency range with a quasi-peak detector, it takes a long, long, long time. The peak detector, we can do it in a few seconds. So we generally do our work with peak detection mode and then check with a quasi-peak that if we've reduced the peak, say, by 5 dBs, that the quasi-peak has also gone down by 5 dBs. Now, mostly, that's the case. That's what happens. Occasionally, though, in certain circumstances, maybe we've done something with filtering which hasn't increased the amount of energy absorbed. It's just spread the energy over a longer time. Say a transient, spread the transient energy over a longer time. The quasi-peak detector might integrate that to measure the same thing. So although our peak detector measures less, quasi-peak detector measures the same. I've seen that happen once in the last 23 years. So it's not a common occurrence. Generally speaking, in a proper test lab anyway, the quasi-peak detector always measures less than the peak detector. So it helps to have a quasi-peak detector on your analyzer, but I don't think it's essential most of the time.
Okay. One more question. When using close field probes to check emissions in serial manufacture, how many dB worse can a product be from the one that passed the lab test and still be acceptable for sale?
Well, remember that we're doing signature checking. Okay, so we've got a signature for the one that we know passes the test when done in a particular lab in a particular way. And we should have those results in front of us. Where you've got, say, 10 or 20 dBs below the limit line, talking about emissions, then you can stand 3, 4, 10, maybe 12 dBs variation in your close field probe reading compared with the signature around that frequency range. But if you've got a particular frequency which is close to the limit, and often it's a clock harmonic, then maybe we can't stand more than 1 dB variation. If we measure that the noise has gone down, the emission with our close field probe has gone down, well, that's good. But if it goes up at all at that frequency, then we have to dive in and do some more careful measurements. In fact, it's a bad thing to be that close to a limit line anyway, because of tolerances, natural tolerances that you get due to variations in components and wiring and stuff like that. It's always a good idea to have a 6 dB margin below the limit line. In other words, draw a limit line, your own limit line, 6 dBs at least, maybe 10 dB, below the one you want to pass on a compliance test, and make sure that on a compliance test you're at least that much lower, and it'll give you a lot more flexibility and a lot more, what's the word, resilience, that's a good word, in manufacturing, because you don't have these particular frequencies that are close to being non-compliant. I hope that helps.
Okay. We've received so many great questions we'll try to address in the future. Keith, thank you again for your time and expertise. Attendees, if you liked our webinar, join us this October for EMC Live. This is a brand new online multi-day event hosted by Interference Technology. This event will feature roundtables, webinars, and panels on everything EMC related. You can visit emclive.2004.com. 2014. Let me say that again. emclive2014.com for more information. If you have any more questions we didn't answer here, please send us an email at info@interferencetechnology.com. A recording of this webinar will be available on our website. We'll also send a link to all participants shortly. Thank you for attending.
Thanks, Belinda. Thanks, guys.
Thanks, Keith.
Cheers now.